But the Earth has this other piece of angular momentum which is just rotating about its own axis, right? So that would be the rotational part, so we need to figure that part out. So we've got the translational part. So basically what we need to do is think about the center mass of the Earth, find the perpendicular distance of every single atom all the way through the Earth to the center of mass or to this axis, add up mr squared for all these things to get the moment of inertia. Well, we don't have to do that. What we'd have to do is we'd have to pick an atom in the Earth, and then we need to find how fast it's going, and then we can get its angular momentum. But it turns out if you go through all that, you find out that rotational angular momentum can be expressed as the moment of inertia times the angular speed, except it's actually angular velocity, and we haven't had angular velocity yet. Well, no, this is any object. So we know what angular speed is, right? Radians per second, 2 pi over the period. So we can actually derive this. I'm not going to do it. But what do you think? What do you think the direction of angular velocity would be? Well, suppose, okay, so let's talk about, we talked about moments of inertia and things rotating, and we got rotational kinetic energy, right? Rotational kinetic energy was half moment of inertia times the angular speed squared. And so suppose we had a disk that was spinning on its axis, and we knew the angular speed omega, and we figured out the moment of inertia of the disk. We could calculate that. What do you think we're going to call the direction of angular velocity? Yep, right-hand rule. That's right. So if it's rotating around the axis like this, then the direction of angular velocity is just given by the right-hand rule. Curl your fingers in the direction of rotation. Angular. Okay, so the Earth is, so here's the Earth. Its axis is actually, its axis is actually not quite perpendicular to the plane of the orbit. There's about a 23-degree angle there. So the Earth is spinning like this, so we'll say it's going around this way, which means that its angular velocity is going to be up this way. Okay? So presumably the magnitude of its rotational angular momentum is just the absolute value of I times the magnitude of the angular velocity, which is, of course, just the angular speed. So we need the moment of inertia of the Earth, and we need its angular speed. So what we're going to do is look up the moment of inertia of a sphere rotating around its center. And that turns out to be, and this is just done by using calculus to add up all the mr squareds. So it's m total r maximum squared times 2/5. And now we need to figure out the moment of inertia of the Earth rotating around an axis around its center. And then we need the angular rotation speed. So let's get the angular speed of the rotation first, okay? So how are we going to do that? Distance over time. Well, distance, angular speed doesn't have units of meters. All right? So angular speed, radians per second, right? Radians per second. So which equation are we going to use to calculate the angular speed of the Earth? Which of those equations is the right equation? Remember, the mass of the Earth is 6 times 10 to the 24 kilograms. The radius of the Earth, we better look up. 6.4 times 10 to the 6 meters. Think about the units. Which one's the right equation? What are the units of angular speed? Yeah, so we better have radians on the top and seconds on the bottom. Well, so how many radians does the Earth rotate through in one period? 2 pi. So what should be in the numerator? 2 pi. And it takes 24 hours, so what should be in the denominator? That many seconds. 24 hours times 60 seconds, 60 minutes times 60 seconds. So let's look at, this has the right units, radians per second. So let's figure it out. It is 2/5 times the mass of the Earth, which is 6 times 10 to the 24 kilograms, times 6.4 times 10 to the 6th meters squared. So that's the moment of inertia. And then we have the angular speed, which is 2 pi radians divided by 24 hours, 60 minutes per hour, 60 seconds per minute. And what does that come out to? 7.5 times 10 to the 33rd. 7.15. Well, that's 7.2. Let's not get excited about significant figures here. So kilogram meter squared per second. So let's write this over here. We have the rotational angular momentum is 7.2 times 10 to the 33rd kilogram meter squared per second. So how do we get the total angular momentum of the Earth? Add them together, but yeah, they're in different directions. Uh-oh. So we actually have to add the vectors. So it turns out that if you so the angular momentum of the Earth about its axis, if it's this way, I think it turns out that the translational angular momentum relative to the sun, which is over here, is actually that way. So that's, and this would be, so we'd actually have to add the vectors to get the right answer, and so we'd be adding a big vector, which was L trans, to a much smaller vector, 10 to the 7th smaller. So to get the total angular momentum of the Earth going around the sun. Questions about that? Okay, so let's look at a couple things and think about what's going on here. So what we've got here is it's a disk. It's rotating around its axis. What does the arrow represent? Angular momentum, right. What kind of angular momentum? Well, vectors can't be positive or negative, so it's on the plus y-axis. But is it translational or rotational angular momentum? Rotational. So what should happen if we just make it rotate slower? It should get smaller. What happens if we make it rotate the other direction? Arrow should point down, and if it goes faster in the other direction. Okay, so that's basically what's involved with that. Not very surprising. Well, is it rotating around an axis that goes through its center of mass? That's why. That's why. So here's something that has rotational angular momentum. Could it have translational angular momentum too? So relative. So pick a point that it's going to have translational angular momentum too. Okay, his head. So now does it have translational angular momentum? It does, doesn't it? But I was actually going in a straight line almost. What happens if I walk in a straight line? Well, what does the definition say? The definition says it would have translational angular momentum because we just have to take R cross P and we get some translational angular momentum. That's interesting. So what would that mean? Well, consider the following situation. So here's some object that can rotate around its center, so it could have rotational angular momentum, although it doesn't at the moment. So this is a little ball of clay up there that could fall straight down and hit it. And then, would it turn? Probably, huh? Probably. So, okay. So now, does this system have rotational angular momentum? Sure it does. Now consider the system of the clay plus this spoke device. Suppose we have, so we consider initial angular momentum from the minute the clay starts to fall. So here's the clay falling. When the clay was falling straight down, did it have any angular momentum relative to the center of the wheel? It did, didn't it? It did, didn't it? And so we had an R cross P that was out while it was falling. And now this whole thing has angular momentum out. And we suspect that actually the angular momentum of the system now, clay plus ball, is actually the same as it was when it was falling straight down. So it kind of makes sense. The ball had some translational angular momentum. And now the system has rotational angular momentum. The ball actually still has some translational angular momentum because it's orbiting the center. So maybe the angular momentum of the system before and after was actually the same. Maybe it makes sense for something falling straight down to actually have angular momentum. Now we're going to see that a torque, a twist is needed to give something, and twist from the surroundings is needed to give a system angular momentum to start with. So the angular momentum of this wheel is essentially zero, and I need to apply a torque to give it angular momentum. I'm part of the surroundings. But in that case, both the ball and the wheel were part of the system, and so it does make some sense for it to have some angular momentum. Let's look at another kind of system. It's a dumbbell, color-coded so we can just see what its orientation is. So two massive balls attached to a low mass rod, which is attached to another low mass rod that's pivoted on the center. So let's think about what kind of angular momentum the system has. Okay. Well, okay, think about it. Think about it. So the system is the dumbbell. The point about which we want angular momentum is clearly this pivot. Okay, let's think about what kind of angular momentum that device had. Okay, so you saw it moving. We're considering the pivot in the center. What kind of angular momentum did it have? The system is the dumbbell. Okay, so translation. So most people said rotational angular momentum was 0. Some people said translational angular momentum was 0, but mostly. Okay, an interesting thing to do is to actually have the balls leave trails. So let's look at trails. So is the dumbbell rotating around its center of mass? No, it isn't, is it? Because the red ball is always above the blue ball. They never switch places. Okay? So no rotational angular momentum because it's not rotating around its center of mass. Translational angular momentum because the whole thing is, the center of mass of the dumbbell is orbiting that center point. Okay, what would have to happen to give it rotational angular momentum as well? So let's show the angular momentum. What? The balls would have to rotate. So let's see if we can make the balls rotate a little bit. We'll make them. Okay, I'm going to leave the trail on, but now that's interesting. Does that have rotational angular momentum? Well, look at the dumbbell. Is it rotating around its center of mass? Do the balls ever change places? Oh. Well, now the blue ball's on the bottom, and now the blue ball's on the top. So, does it has rotational angular momentum, doesn't it? Now it just happens to be that the period of that rotation is exactly the same as the period of the other rotation. So now that may be easier to see. Okay, now it's got both, right? Rotation plus. So what are the directions? What's the direction of the rotational angular momentum? Plus C? Plus C. Okay, what's the direction of, what did we just say? Rotation was plus C. What's translation? Plus C. Okay. So what happens if we lock it this way? I'm hearing just translation from the front. You guys agree? Yeah, because the balls aren't changing places. But now, yeah, now the balls are changed. So it's rotating, and we can make it. Oh, that's interesting. Now it's rotating the other way. So what's the direction of the rotational angular momentum? Plus C. Rotational angular momentum? Negative Z. Translational angular momentum? Okay, so let's turn on the vectors and see if we agree. See if the calculations agree with what we just said. Okay, so that's rotational. No, sorry, translational angular momentum, orbital angular momentum, right? And it is plus Z, as you said. And it looks like there's no rotational angular momentum. So now we'll let it So actually, does have rotational angular momentum, but not very much. Look how tiny that arrow for rotational angular momentum is here. But the balls are, so let's make it rotate a little faster. Okay, now it looks like the two kinds of angular momentum are in the same direction. So that's kind of like the Earth going around the sun, all except the Earth's axis is tilted a little bit, so it isn't quite. Okay, so now it's locked again. Looks like no rotational angular momentum. But now we'll let it... Oh, look at that. Now it's, as you said, rotational angular momentum and translational angular momentum are in opposite directions. So one is plus c, the other is minus c. So what do you mean L? They're both L. Which L? Oh, the total angular momentum. Total angular momentum. Well, let's see. So the translational angular momentum looks like it's plus c. Rotational angular momentum looks like it's minus c, but it's smaller. So we're going to get a net angular momentum in the plus c direction, right? Okay. Okay, how would we make them equal each other? It'd have to spin really fast, wouldn't it? Or orbit more slowly. Pick one. They'd have to spin really fast. Spin it faster. Okay, let's see if we can spin it faster. Is there an omega in here somewhere? Let's see. Okay. Let's see what happens there. Whoa. I think we changed the wrong one. Okay. That looks like the wrong one to make faster, so we'll do it that way. We were inside the arrow, actually. So is that what you wanted? All right. It's fast. All right. Okay. So we've calculated rotational angular momentum. We've calculated translational angular momentum. We've added them together. The only thing left, and we're not going to really do it, just a preview of what we're going to do with that, is changing angular momentum. And to change angular momentum, we need this thing called a torque, which basically means applying a force in such a way that there's a twist. Okay, so if I hit the center of this, not much happens, but if I hit the edge of it, then it spins, so I must be applying a torque. And to apply the torque, there's some vector from the center. It's a torque about this axis, vector from the center, and I apply a force in a direction that has at least one, well, I am applying it perpendicular because this is a circle, and that's the easy thing to do. Okay, and what happens if I apply the torque the other way? Slow it down, won't it? So that's the basic idea. Torque, actually, you're not going to be real surprised. Okay, the symbol for torque is a Greek lowercase tau around location A. And it depends on the force, right? But what else would you think it would depend on? Can I exert a torque here? I can. Yeah, but the farther away I am, the better it works. So that vector from the center, so we have vector, we have a force, and what do you think the direction of the torque I applied here was? The force is this way, the vector, yeah, what? Yeah, the same direction as the direction I'm giving it angular momentum, right? So vector R that way, force that way, torque up, looks like another cross product. So you get to use cross products again. And so all the usual things, you can calculate magnitudes, you can calculate directions, and here's the punchline. So let's see how many different ways we can think of to write this. Suppose we say L initial or L final equals L initial plus torque around that location times, what do you think? Time, delta T. Or we could write change in angular momentum around some location is torque times delta T. We can write, what do you think dl dt is going to be? Yeah, so what do we do with this equation? Net torque. In fact, we better have a net here. And just to round it out, the change of angular momentum of a system plus the change of angular momentum of the surroundings is going to equal 0, the conservation law. So we'll spend some time next time changing angular momentum, but it's often useful to define our systems kind of carefully so that there is no net external torque about a point, and that makes it easy to solve final equals initial problems.